Hey everyone, so I know last week's homework was kind of hard, so I wanted to go over what I did, to kind of share with you guys my process and maybe we can learn from each other. Then also I have maybe potential for collaboration at the end. So starting out with, I'll just go through the questions I guess. Starting out with number 1, what is a Feistel cipher? What are critical components? So with this one, it seemed like most people got this. I learned what I learned from the reading from week 6 and 7. But basically, a Feistel cipher is something that uses a function to implement confusion and diffusion on a generic level. So with that in mind, there are a few key steps that can kind of do this. When you think of, let's see, expansion of the key using substitution, reordering the key using permutation. These are kind of examples. And some of the key components would be, let's see what I wrote here, your key size, your block size, various variables like that. Alright, so number 2, for this one, I wanted to understand better what DES does. So to do this, I needed to basically do a mapping so I could kind of understand structurally what it's doing and then what it's doing inside each round function generically. So that's kind of what I explain up here. So if we start here, I'll kind of walk through what DES is doing at a high level. First of all, you start with a 64-bit plaintext. You go to initial permutation of your plaintext, and then you then split it into 2 bits, 32 long bits. The first 32 go left, and the second 32 go right. And from there, you'll do what's known as the round function, which will have an unique round key. So round key should be 48 bits, and then your round function will first take your key, turn it from 32 to 48, because something similar happens to the key. Then from there it'll expand your ciphertext. Then from there you'll use the S-box to substitute the right half of it, basically using an XOR. Then you'll do a permutation on the resultant of the XOR with the key. So basically what's happening here is you expand key, expand ciphertext, XOR key with the right half of the message, substitute the S-box, and then XOR S-box, oh wait, I'll actually do a permutation, then XOR that with the left plaintext. And that'll be the output right plaintext. Well, the left plaintext is just going to be, output left plaintext will be equal to the input right plaintext. So from there, after doing 16 rounds of that, you'll have a final permutation, which is the reverse of the initial permutation, and then you'll compile it into your 64-bit ciphertext. So when your keys are both zeros here, well, your key and your message are all zeros, what's happening is your initial key will be 64 bits of 0, initial plaintext is 64 bits, initial plaintext permutation 64 bits, because it all be zeros. It doesn't really matter. The order would change if they were various values, but since they're all zeros, you can say it's the same thing. Then you split. Round 1, you will expand, like we saw. From there, you will shift it, because it's round 1, so you'll shift it 1 key. You'll XOR with the right ciphertext. Then you'll do an S-box substitution. So this is the result of the S-box substitution that I got. Then you'll do a permutation. Again, this is the result of permutation. Then you'll do XOR of that with the initial value. So it's all zeros. It'll just be the same thing as it was before, since 0 XOR something is just going to be that thing that you're XORing with. Then the current left value after the round is just all zeros. The current right value is this. Int of right round 1 is this. And int of right round 1 left is this, kind of just being explicit over there. Then I converted it into hex, which isn't really required. I also included my S-boxes that I used. These are the standard S-boxes that you can get from notes. And then I also included my permutation table. Then I also did this programmatically to verify the results, so I will show you the code for that. I had to use code from Geeks for Geeks to really understand this. So there's a few helper functions, one that converts to hex, binary, binary to hex, binary to decimal, decimal to binary. Then I have a permutation function, which basically rearranges the values based off the value of my permutation table. Then finally, I guess we have our shift, well not finally, but next we have our shift value, which shifts the keys based off whatever round it is. And then we have our XOR, which is the XOR function. Then we have our initial permutation table, and we have our, which will take 64 bits to 56 bits. Then we have our expansion D-box, which will expand the key. Then we have a permutation table, which will be the round permutation of the result. Then we have our substitution boxes, as I showed you from notes, for my submission, and our final permutation value, which is the inverse of the initial permutation. This is where all the magic happens. What happens is I will take my input, I'll convert it all to a hex value because I have to process less, so it's kind of an efficiency decision. From there I will do a permutation, and for my initial permutation I'll split left and right. I will then perform 16 rounds. So first I need to expand the right half to 48 bits. Then I need to do an XOR the right expanded with the right round key, or with the round key. Then from there I will do SBox substitution of each hex value. There should be 8 because of how the expansion works and how hex works. So there will be 8 rounds, 8 SBoxes that are unique. So from there you'll create an SBox string, which is the permutation of SBox with that permutation value I showed you above. The result you will then XOR with the left, and then left will equal to the result, which will pretty much just be the left, and then you will end up swapping them in this implementation. At the end, you of course combine them, and then you're going to have to do a final permutation, and then you'll return whatever that final permutation is. So that's how the code works on a high level. Okay, so moving on to part B. It's pretty much the same process, but the only difference is there is a 1 somewhere. So when you change it to the 57th bit, ultimately the left will still be the same, but the right will change with 1 value. So it'll go from a 5 to what originally was a D. It's kind of funny how that works. So the round key is also 0, but the difference here when we see them in binary is just a 0. So that's the only difference, which is really interesting. But I guess that's how powers of 2 works. Okay. So moving on to part 3, define and distinguish among groups, rings, and fields. This one is pretty basic. Essentially, you just need to get properties of groups, rings, and fields. The general relationship between the three is rings are groups and rings, fields are rings and groups and fields, while groups are only groups. Similar to geometry, where a rectangle cannot be a square, but a square is a rectangle. It's a one-way relationship. You'll see that kind of the ring is an expansion of the group, and the field is a further expansion of the ring. Okay, so moving on to number 4. Define finite fields in the form GF of P. So what this is saying is this is going to be a Galois field that is a prime Galois field, meaning every value will have an additive inverse and multiplicative inverse. From there, we can also say that the domain of GF of the P is going to be from 0 all the way to P minus 1. And I also defined some operations of this Galois field in my submission. I said A plus B would be C mod P. A minus B is A plus negative B, which is going to be equal to D mod P, because it will be a different value than before. A times B will be E mod P. A times the inverse of A will be 1 mod P, which are just general properties. So I also defined an example. When it's 7, the domain will be from 0 to 6. And then here are some of the operation values. This will be the result of the operations, just substituting P for 7. So that's kind of just generally what I was conceptually asking. For number 5, there's a lot of right answers here. Generally, but as long as you're using your modulus operator and you say what it does, I think you get it right. Okay, this one was one of the more fun ones. You see really a lot of screenshots here. This is from my code. I decided to do it in a code-based implementation, so that's what I'll review. So let me go to my code. So my code implemented here, I used a class called a Galois field, and I defined some methods. There's an initializer method, which basically creates some properties. The thing that we're interested in here is self.in, since in is going to be from p to the m power, 0 from p to the m. Then I have a toString, which says all the elements. Then I have something that calculates the additive inverse. And due to the nature of this being a modular arithmetic, there may be multiple right answers. I did what I thought was correct. So what I did is I normalized the value. So it'll be from 0 to 112 in this case, because we're using 113 as our test value. Then from there, if the x value is 0, then we should return 0, since 0 plus 0 will indeed equal 0 mod 0. Whereas in the else case, you need to do whatever the max value is minus x, because that's what will output to 0 mod 0. So if if I go to my example here, I want to explain these print statements first. So for the additive inverse, calculating this, I had to realize that the output should always be 0 mod 0. And this is a property of the additive inverse. When you do a plus the inverse of it, it'll always be 0. So from there, what this code is essentially saying is when here's my result that I think it is, and the reason I think it's my result is because this plus this, the value that you're trying to find the inverse of plus the inverse is equal to the modular value, so that plus the other value mod, and then the max value 113 in this case. So that will be equal to 0 mod in, and if that's the case, then you are correct. So from there, we go on to calculating the multiplicative inverse. Before we do that, we need to understand GCD. So this is a function that calculates the greatest common divisor, whatever, I forget what it stands for, but it calculates the greatest value of that. And in this scenario, the value should always return 1. If the value does not return 1, then we don't really care what the multiplicative inverse is because it doesn't exist. So GCD, all this is doing is if the value is 0, then return 0. That's an edge case. Otherwise, just iterate through all the way up to your current value and find the thing that is the greatest common divisor. And it should be 1. If it's not 1, then you got a problem. Well, not really, but this does work for situations where it's not 1. It'll just return a value other than 1, so that's fine. If we look at this, I implement GCD, I store it as a variable, and then from there I say if it's not 1, then there is no inverse. If it is 1, there is the inverse. We're going to say t is equal to 1 because we need to calculate our t constant. And so while this condition is basically saying while the max value times t plus 1 is not completely divisible by the value that you're trying to find the inverse of, then keep incrementing t until it is. And that's how you find your t value in kind of a brute force way. And then finally, to find the solution for this, all you need to say is the max value times your current value of t plus 1 divided by your value you're trying to find the inverse of times the modular value of self.in. So this is going to be explicitly 113 times t plus 1 divided by, let's say, 0. So I think t would be 1 in 0's case. So you'd say self.in plus 1. Well, I guess 0 would be 0. So let's do 1. So we do where x is 1. So you'll have 113 times 1 plus 1. Okay, so you have 113 plus 1, which is 114. Then you divide it by x, which is 1. So that's going to be 114. Then you do mod n. So the inverse would be 114 modulus 113, which equals 1. So that is our actual condition that we need to test. You found the correct multiplicative inverse when the condition is true that the value you're trying to find the inverse of times the inverse mod the max value is equal to 1 mod max value. So I will run this code and you will see the result. Alright, so it's doing a quick installation of something real quick, but we see the code runs. So this bottom part is the additive inverse. This will be kind of the result, where the additive inverse is 112, 111, all the way down to 1, and it starts at 0. The reason it starts at 0, not 113, is because it's modular arithmetic, and 113 mod 113 is 0. So that kind of makes sense to me that it starts at 0 and then does 112 all the way down to 1. From there, on multiplicative inverse, this one is a little bit more abstract, but as long as you had the basic formula, this should be your output answer. And maybe you're a little confused on how I derived the formula. Essentially, the formula was derived from a few principles. First, you need to understand the phrase 1 equals xs plus nt, because this is what you need to calculate, since s in this scenario equals x to the negative 1 mod n, which is what you're looking for, right? Like you're looking for that s value. So from here, you just need to adjust this first line a little bit so you can solve for x. So what you can do is you can say in the end, s will be equal to nt plus 1 divided by x. And these are all values that we can know or calculate. So my code, like it did, it implemented this by first calculating t, a valid value of t, and then implementing the values that we did already know, which was n and x. Again, n being the max value and x being the value you're trying to find the inverse of. So with this, that's all you really had to calculate for the multiplicative inverse. And these are just kind of me explaining my results. From here we have 7. You see an 8 here. That's because I had some weird formatting thing I couldn't figure out, so I just put a 7 in front of it. I hope they don't mind. So yeah, so basically this is just doing des function. And you're first encrypting with specific outputs of the f function. And so the first scenario is when the f function only outputs 32 bits of 0. And the second one is where the f function only outputs r, whatever was input into that function. So it's kind of abstract and it's very theoretical, but what I got was I had a random bits that were 0 1s that was 32 bits long. Same with the right for the sub key for the sub ciphertext. Then from there, my key for that round, I say key of n, but key n is going to be like a number from 0 all the way up to infinity. I guess here all the way to 16. So I say k of n, so it'll be k of 0 in the scenario down here, but it was a key that is 48 bits long and 0s and 1s. So for the any value, since generically L1 or Ln plus 1 is always equal to Ln, Ln plus 1 is always equal to Rn, where Rn plus 1 is always equal to Ln XOR the f function of R, where R is going to be various input. So in this first case, it'll be R0 XOR K0, but since f is going to output all zeros, then we're just going to get L0 XOR and then 32 bits of 0, and since L XOR 0 it's always going to be whatever is it being XORed with the 0, it's going to be L0. So this R1 will be equal to L0. So they just swap, which is really nice. And then for number 2, F output R. Okay, so in this scenario, let's say we have the same definitions, and then from here we have a little bit different math. So L1 is still R0, and R1 is going to be L0 XOR and then the f of R0 K0. So f function of the scenario will always put out R0 K0 XOR R0 XOR K0. So it'll be L0 XOR R0 XOR K0. From there, I'm not sure if you can simplify any further. If you can, you would probably need some sort of specifics, but that's as simple as you can get it theoretically, I think. Okay, now B is just a reverse. But since des is a symmetric key cipher, you're doing the same thing, but with different kind of constants. So the only thing that would change in application is the values, whereas in theory, nothing changes, which is quite beautiful. So it mentions these properties used. You can't really use much of them. I only used one property in the previous one. I also used it down here again since it's the same process. So as you notice, same as above, but instead of 1, it's R16 and R15, since you're going in reverse. And then for this one, for 2, R output 0, literally the exact same thing, different constants. So that's kind of how the homework works. If you guys want to have maybe deeper discussion, I am trying to implement des in its full application. So I'll take a bit of an inspiration from this code, but I want to implement my own version that I think could maybe be a bit more efficient. So if you want to work on that with me, please let me know. Just add me and group me, and I hope this helped.